Hello everyone. What is our process? When a supernova collapses and blows up, it produces a large force of extremely fast neutrons, forming a rapid neutron capture process called R process. Iron is used as seed nuclei to continuously capture neutron, and beta decay releases beta particles and neutrons will be released until radioisotope nuclei can accommodate more neutrons. The 黑色箭头 which will become the next heavier element, and the heavier element will be produced again and again. 那个平行的黑色箭头 when the neutron force decreases, the R process stops, and the radioisotopes nucleus on the R process will generate beta decays on its stables， 是比较浅色的斜上箭黑色箭头。那左下角的话呢，就是 R process 的它一系列的反应过程，它就是铜加5个中子，最后会释放出一个，就是产生一个新的重元素，然后它会释放一个贝塔负粒子。Next one, what is S process? The slow neutron capture process occurs in asymptotic Jan branch star ray line. In the black frame, where is a steady but not large supply of neutrons from nuclear fusion reaction in stars. Therefore, the neutron capture speed of S process is much slower than that of R process. When the C nuclei capture neutron to form an isotope with a higher atomic mass. 又比较浅色的平行黑色箭头 E is unstable. It undergoes beta decay and releases beta particle to form elements with the net atomic number of electron capture, which means a electron captured by proton and become neutron, making the nucleus turn excited state into ground state. The process is slow, hence the name, in the sense that there is sufficient time for this radioactive decay to occur before other neutron is captured. Where to find the respective nuclei on the chart of nuclei? First, we talk about the R process. In the gray up of red frame indicate the product of the R process back to the band of steady or black box by beta decay. Additionally, the respective nuclei of S process indicate the product of the S process back to stable state by the electron capture or beta decay. And last, the green line tells us both processes start with a nuclei with the iron 56.
后面有说到，这中子的通量降低的时候 ，R process 会停止。为什么会停止？
因为那个中子通量减少了，然后 R 反应，因为它是一瞬间有多个通量的那个单位截面积的那个中子通量会进到那个原子核里面，然后就会产生一系列的裂变。但是它现在的因为超核心爆炸结束了，中子通量也就结束了。
那个上面有提到说，超新星在爆炸的时候，它会喷散出那个元素，它会是以哪一种形式散出来？
不知道
就在影片里面有提到，它可能是会以那种洒水器那样子的方式发射出来，这样发散，所以我们才会看到那个星云长那样子。
So Steve, what are the white box and the black box here? Can you explain? And also the white box with dashed line.
那黑色的虚线大概就是它那个在 R process 过程中，它一系列的裂变会产生的。那这个实线的方框呢，就是大概是 R process 中子通量结束后，它就会慢慢贝塔 decay， 然后形成最稳定，就是因为根据热力学，物质都会倾向最稳定的状态形成，存在于这个宇宙中，所以它会就是像我刚刚说的，变成最稳定的状态。黑色框这个的我就不太确定。
You can see what's written on the graph.
是从 R 过程制造的。
It shows you that the stable isotope produced by our process at the end tend to distribute at the lower right of the band of stability because it decays from this direction. Last week, we talked about HR diagram. In the previous assignment, I was hoping that you can explain this using our sun as an example. So one of the questions in the assignment was, can you explain how the sun will change its location on the HR diagram? That was one of our questions. Because that was a detour to the HR diagram, let's come back to our original topic, which is element formation in stars, because the topic here is not just astronomy. We are more concerned about how elements or nuclides were formed in stars. So let's come back to this topic. Key concepts in stellar evolution. Stars form by contraction of massive clouds of gas. We know stars are made of gas, basically. This gas was driven by gravity, because we know gravity is everywhere. Mass and distance are the key parameters determining the force of gravity. And as the cloud contracts, all its energy is confined to a smaller volume, and it heats up. You can imagine that it's a little bit like conversion of the potential energy of water at a higher level. When it goes down, it converts its energy of potential energy to kinetic energy, and this usually leads to heat. So you can also imagine that when the star gradually converge, the cloud of gas converge to a smaller volume, its potential energy will be converted to heat. So it keeps contracting because of gravity and heating up because of conversion of potential energy to heat until some force operates to offset the gravitational contraction. Otherwise, it will just continue to converge and converge. So some force will operate to offset this gravity. So what is that? It is the radiation pressure generated during nuclear fusion. So nuclear fusion will create a lot of heat. And this is the source of radiation pressure that will go against gravity. So you can imagine if you see a star, its physical presence, then it means it's under a hydrostatic equilibrium. 静力平衡。它是在一个平衡的状态下，你才会看到它。Otherwise, you will see it expanding or contracting. That means it's not in equilibrium. If it looks like the same today and tomorrow, and the day after tomorrow, then it means it's at equilibrium. And this equilibrium will be reached when gravity is balanced by radiation pressure. So let's talk more about nuclear fusion. We talked about this when we talked about the fundamental forces last time. These are two hydrogen, H2. So we see P1N1 and P1N1. And these two atoms, they tend to repel each other because of electromagnetic force. We talked about this last time. Imagine there is gravity pushing these two atoms together. And when these two atoms, they were pushed close enough to each other, then the third fundamental source will kick in. That is strong force. So recall, what is strong force last time? It is the force that sticks the protons together. Ultimately, these two atoms can fuse to form one new atom if there is a loss of mass. And indeed, if 2H2 is fused to form one helium-4, the mass loss is 0.025 gram per mole of reaction. Sorry, I shouldn't say per reaction. And this is equivalent to this amount of energy. So that's actually very massive. Because of nuclear fusion, the consequence is a lot of heat. Then this will create some radiation pressure that go against gravity. So that's the chain of reaction out there in stars. So you can imagine it's actually the equilibrium between gravity and pressure, radiation pressure. So more about energy consideration. Here we have two sets of elements. So this set of elements is smaller. It has 2 protons, so I guess it's helium. And these 2 sets of elements has more. So you can imagine that with the larger element, the electrostatic force against each other will be stronger when the nuclei are larger. So we are actually doing the argument backwards. You will need higher ignition temperature for the synthesis of heavier elements because the repulsion here is stronger. So you need more energy. If you need more heat, that means higher temperature to start the nuclear fusion, then that means you need more potential energy because we said in previous slide, the heat comes from potential energy. So we need more potential energy for the stardust to reach a higher ignition temperature, which is needed for the nuclear fusion reaction. Therefore, we need larger stars to offer higher potential energy. So in short, we need larger stars to fuse larger elements. This table is from the textbook. It tells you what is the ignition temperature, IGT is ignition temperature, needed to start this nuclear fusion reaction. Fusion of hydrogen will form helium-4. Helium will form carbon and oxygen. They are fundamental to life. Fusion of carbon will form neon, magnesium. Fusion of oxygen forms silica, the fundamental material of Earth. And fusion of silica ultimately leads to iron. These are the respective ignition temperature. And as I mentioned last time, I asked around, do you know what's the highest temperature in a normal, regular chemical laboratory? So the general temperature is 1,000 to 1,500, temperature around this range. And look at this. This is MK. What is M here?
I guess million.
How many zero after?
10 to the power of 6.
Very good. You can see that this is very, very high temperature out here. And these are the respective stellar mass in the unit of solar unit. So 1 means like the mass of our sun. Fusion of hydrogen to helium has very low threshold. Very small stars can do it. Like you only need to be 10% of our sun, then you can do it. However, if you want carbon and oxygen, you need at least twice the mass of our sun. If you need more, you need larger stars. So there is a straightforward relationship between the elements you want and the mass you need. Based on what I just said, the relationship between the elements that can be fused in a star and the mass of a star. Stars of different sizes are also different element factories. This is a small star, like 0.1 solar mass. In this kind of small star, what they are doing is just fusing hydrogen to helium. If it's a little bit larger, like a 2 solar mass, then it will have maybe 1, 2, 3, 4 layers. I will explain this later because our sun can also reach this stage at its red giant stage. Lastly, if it's a very massive star, like a 15 solar mass, it has multiple shelled structure. It's a little bit like our ocean. Our ocean is also onion-like. It has several layers. 我们的海洋也是洋葱一样一层一层的。And the stars is also layered, or is pretty much like an onion. Nuclear fusion has an end. It will stop at iron 56. This figure, this is mass number, and this is the binding energy per nucleon. This is not from astronomy, this is from physics. If the binding energy is higher, the more stable the nucleus will be. And then they realize that of all the elements, the element that has the highest binding energy per nucleon is iron 56. Why? I don't know. You can view this as an experimental result. In this direction, it means more stable. In this direction, it means less stable. The mass of nuclei heavier than iron it proves to be slightly larger than the mass of the nuclei that are merged into to form them. No mass loss. That means if we want to fuse larger elements here from iron 56, then it's no longer spontaneous. Why? Because during the fusion, there is no longer loss of mass. You need to input more energy into the system to force two elements to fuse into a larger element. This is no longer favorable. All the nuclear fusion will proceed in this direction and stop there. Then you might ask, how come we have so many elements here? How are they formed if nuclear fusion stops here? That is your assignment. These are some physics that we need to know in order to go further into nucleosynthesis in stars. We want to now switch back to HR diagram. In the main sequence, most stars spend the majority of their lives fusing hydrogen to helium in the core. It's the so-called main sequence stars. Their route to demise, demise means death, depends on their mass. So they will die in different way. So you see these lines. That means they will die differently. We start with a very small star, like a star with only less than 50% of our sun in mass. This kind of stars, they are also called brown dwarf, 褐矮星, or red dwarf, 红矮星. The low mass stars are likely to be fully convective. That means like this. It's a little bit like if the pound is very small, then it's very likely that it can be fully convective. But if the pound is very large, the pound can be layered. And this star is very small, so it's fully convective, like this. There's barely any layer inside the star. Therefore, there is no shell burning. Because there is no shell burning, there is no red giant stages. Later on, we will explain the giant. Why we will see giant? Because there is so-called shell burning. But in small stars, we don't see this. So they spend their whole life burning hydrogen. The procedure can take very long. In fact, smaller stars live longer than large stars. At the end, they will turn quietly into white dwarfs. So whenever I read this, I feel it's a bit like philosophical. It's a bit like a human, right? Now let's take a look of our sun. Our sun is probably in the middle. It's not too small and not too big. Its route on the HR diagram is like this, counterclockwise. So what happened? Initially, it's fusing hydrogen into helium. When it enters a subgiant stage, its inert helium core is getting larger. Because initially, the burning area is more at the interior of the sun. However, when the internal fuel is used up, the inert helium core will pile up. And this inert helium core means they are not reactive. So the burning area will be closer to the outer part of the sun. And when this happens, the heat zone is closer to the surface, so the sun will expand. That's the reason we enter the subgiant stage. And later, when most of these hydrogen is used up, it will then enter these stages. In these stages, helium starts to burn, because most of the hydrogen, except for the outermost one, is used up. Once the hydrogen is used up, the inert helium will fall down because of gravity. And when the helium falls into the center of the star, it will be ignited. And when it is ignited, it will start to burn. So now we have a helium burning core. While at the outer part of the sun, hydrogen is still burning, but it is now no longer in the internal part of the sun. So now we have two layers of burning. Later, when the whole process goes on, helium will gradually be used up from the internal part. We will have an inert carbon core. As said, helium-4 is fuse into carbon or oxygen. So now we have an inert carbon core. At this time, the helium burning part will be at the outer part of the sun. Helium burning is now no longer in the core, but at the shell. And while hydrogen is also burning at the outermost part of the sun. So it has multi-layer structure now. And when this happens, it will become red giants. Why is that? Red giants, products of shell burning. So now you need to distinguish core burning and shell burning. Fusion of hydrogen to helium initially take place only in the core. When this happens, this will not greatly change the size of a star. However, once a star exhausts hydrogen fuel in the core, nuclear reaction no longer continues. And the core, now made of inert helium, begins to collapse because of gravity. The collapse brings more hydrogen inwards to form a shell around the core where fusion of hydrogen resumes. Resumes means restart. So now we have hydrogen burning shell. The ignition zone is now closer to the surface. This will lead to a higher luminosity. So you see that for red giant, compared to the main sequence star like our sun, it will have higher luminosity because the ignition zone is now closer to the surface. And the near surface heating also causes the outer layer to expand. This results in a larger surface area and lower surface temperature. And surface temperature will be reflected in its color, not its luminosity. That's the reason why, compared to the main sequence sun, the red giant will be closer to the low temperature end, and it will be reddish. So that's the sequence of events that lead to the formation of red giant, which is extremely large. Like this is the sun today. Its surface temperature is like this, and that would be our red giant stage with this size and this surface temperature. Planetary nebula, the term sounds very strange because usually when we say planet, it means celestial object other than stars. Stars and planets are different. However, here we use the term planetary to explain a stage of a star. So why is that? Planetary nebula is a historical term. The term was invented by someone who at that time did not really understand the evolution of a star. What happened to planetary nebula is they are products of star expansion and material ejection. So previously, when we talk about giants, like our sun, at some point it will start to fuse helium to carbon. Fusion of helium to carbon at the late stage of red giant. This reaction is actually extremely sensitive to temperature. How sensitive? It will change proportionally to the temperature to a power of 40. So that's very extreme. A small variation in temperature causes large expansion or contraction of the outer material. If the temperature just change 100 degrees, it will change from here to here. And then if it cools down again, it will come back here. It's pulsating because it's too much sensitive to temperature. This results in large pulsation. And finally, it's large enough to throw off the atmospheric material because you keep doing things like this. Over time, you will lose your outermost material. The deeper layer of the star are therefore exposed. The hot layer will emit UV photons to ionize the ejected material that surrounds the star, like this. This looks like a nebula. Nebula in Chinese is 星云. Planetary nebula 就是行星状星云. However, it has nothing to do with planets. It is basically a star which is about to die at its late age. And these stuff are previously its atmosphere. And it throws away its atmosphere. It's like it's dying, and so it starts to take off its clothes and throw it away. And while it's doing it, the internal part emits sunlight to irradiate the clothes that it threw away. So its clothes is now shining. That is the nature of a planetary nebula. And at the end, when everything is thrown away, The sun is now naked. What is left is a white dwarf. So white dwarf is a stellar remnant, the carbon-oxygen core of a star after it expels most of its outer material. And the ejected material will gradually dissipate into the universe and will be gone, leaving the internal part of the star, which is a white dwarf. The material no longer undergoes nuclear fusion. Gravity will make the remnants denser. For stellar remnants with less than 1.4 solar mass, this is a famous limit called Chandrasekhar limit. Apparently, this is based on some calculation, theoretical calculation. At the beginning, the star mass is 2 solar mass. So if after the planetary nebula stage, it will throw away 0.6 unit of its mass, leaving 0.4 solar mass. Then it will be within the Chandrasekhar limit. What is the importance of this Chandrasekhar limit? It means infinite gravitational collapse can be resisted by electron degeneracy pressure. That means electron doesn't want to enter the nucleus. If the mass of the remnant star is small enough, and when it collapses, because its gravity is not strong enough, large enough, at the atomic level, the electron can stay in its orbit. It will not be forced into the nucleus. This is what we call electron degeneracy pressure. In Chinese, 就是电子简冰压力，就是电子它不会被简冰到原子核里面，因为恒星残骸不够大。So you will see a star with material that you know. Nucleus in the middle, electron at the outer part. This is the material that we know. And white dwarf will gradually cool down and become black dwarf, or turn into type 1 supernova if it accretes mass from a binary companion. I will ignore the latter part. So you only need to know that it will basically cool off. So that's a star with the size of a sun. So it has some climax like this. And this is also very shiny. As a human life, I would say it's good enough. With some climax and then gradually, quietly go away. So now we talk about massive stars. So massive stars, larger than 10 solar mass, they are the major element factories in the universe. They can create a wide array of elements, and therefore they lose mass very rapidly in order to create sufficient radiation pressure against gravity. And large stars are well-equipped factories for nucleosynthesis up to iron 56. They will have onion-like layers. And during shell burning stages, like our sun, when it expands, it will strip off their own envelope. Envelope means the outer part of a sun, exposing the deeper layer, which have higher temperature. This is the reason we call them blue giants. Red giants and blue giants, they are both at a shell burning stage. In the blue giant case, this will expose the internal layer. Once they exhaust their fuel, as the mass exceeds the Chandrasekhar limit, a catastrophic implosion occurs. Okay, so we first talk about massive stars with remnants of 1.4 to 3 solar mass. What was the initial mass? Larger than 10 solar mass. So it burns away more than 70% of its mass, or strip off. They will form neutron stars or type 2 supernova. So I will explain the detail here. At the end of their life, they use up all of their fuels. What happens when they use up their fuels? The gravity will take over. The remaining material will collapse inward. That's what we call implosion. After the catastrophic submarine accident, now you guys know the term implosion very well. So during the implosion, electron capture will occur. It will be forced into the nucleus. This is what we call electron degeneracy. This will produce neutrons and other particles at the core. Originally, the electrons that are happily orbiting around the nucleus, when this happens, they are forced to enter the nucleus. They will merge together with proton to form neutrons. However, infinite collapse is halted. Halted means stopped by neutron degeneracy pressure. That means those neutrons says, no, you cannot force us to merge further. We can resist that. That is neutron degeneracy pressure. Because of that, despite the mass out there, despite the gravity, you can still see material. However, this kind of material is no longer the material we know on Earth because they no longer have electron orbits. They are just a mass of neutrons. Collapse of outer material onto the dense degenerate matter. This means neutron, a lot of neutrons in the core, causes rebound. You can imagine that for a massive star, the remnant is also large. So when the collapse starts, the inner part will collapse first and form a lot of neutrons. And these neutrons, they are extremely dense. However, the collapse continues. The outer material will continue to fall on the neutron. The neutron is a little bit like a brick. So the outer material will fall and bounce back because this is too tough. So they will rebound. This rebound will create shock wave. And the rebounds will accelerate outer material. And this is the mechanism of supernova explosion. That makes you think it's an explosion. But the trigger is actually an implosion. The degenerate remnants are the so-called neutron stars because it is a very special material. It's just degenerate material. So this is the massive star. After all the fuel is used up, gravity take hold, and then implosion starts. And then we have this electron capture, electron degeneracy. So we form a lot of neutron at the core. This neutron star here is like a brick. When the outer material continue to fall on it, it will bounce back. And this bounce back will create shock wave. And then the shock wave accelerate the outer material so that at the end, it looks like an explosion. That's the sequence of supernova explosion. And then that's one of the most famous supernova explosion, the Crab Nebula. So it was even observed by some old Chinese astronomer. When this happens, the shockwave, what really happened is this shockwave helped to redistribute elements to the universe. Otherwise, you and I will not be here. Because if there is no supernova explosion, all the carbon, oxygen will be remain in the star. Do not tell me that our carbon is from the sun. No, our sun, indeed, it can fuse some carbon, but it's only at a very late stage of its life. So the carbon that I'm made of, or you are made of, is from another star, which is already dead. And it throws away its carbon to the universe. And then at some point, our solar system catch the carbon and then made us. So now we talk about the largest star with remnants of larger than 3 solar mass. So that's something we all know. Its remnant is no longer visible. Its remnant is a black hole. For stellar remnant larger than 3 solar mass, neutron degeneracy pressure is insufficient to stop the collapse. So that's the famous Tolman-Oppenheimer-Volkoff limit. So how many of you have watched the movie Oppenheimer? In the movie, there was a scene that they talk about the publication of their paper, which is about this. That's the real expertise of Oppenheimer, who is basically an astronomic physicist. And in this case, the implosion will continue to form a black hole, like this. So I don't know how many of you pay attention to this news. So that was a very large event 4 years ago. The first scientific image of a black hole, which was published in April 2019, which looks like this, right? A donut. In the movie Interstellar, they also had a very nice depiction of the black hole, which obey the physics that we know at that time. This is the summary of stellar evolution. If you are a very small star, you live a long life, quietly, without much up and down, and then you leave. And if you are a middle-sized star, like our sun, you have some up, like red giant, and down, which is, I think, good enough. If you are a little bigger, when we want to say someone is rising star of his career, we would say, okay, he, she is a supernova, because supernova is very shiny. So when a supernova explosion occurs, this supernova will be brighter than all the stars in that galaxy. However, if you are too big, then you might have a catastrophic end, black hole, and no one will see you again. We already talked about nucleosynthesis after the Big Bang, and we talk about element formation in stars. I will show you quickly the neutron capture process. The R process means you have to imagine that the neutron is a little bit like a bullet from a machine gun, like this. So it's really shooting fast on existing nuclei, such as iron-56. The thick arrow indicate the process that's really going on when our process happens. Not this. Why? Because the shooting rate is so high. So the nuclei, they have no break. It's like it's constantly receiving neutrons shot by the bullets all the time. So that's how they accumulate the bullet until the nuclei cannot take it anymore. And when it cannot take it anymore, it will take a break by doing very short beta decay. If after this short beta decay, the nuclei think, okay, I can take more, then it take more. And this one, apparently, it can take more neutrons, so it will absorb more neutron until it saturates. This arrow, if you read the figure carefully, this actually happened after our process. Because this takes time until the nuclei gradually decay to the stable isotope. So these are the stable isotope produced by our process. For S process, as mentioned, it's produced in a supergiant. And it's very different. You don't see the thick arrow because at this time, there's no machine gun shooting bullets. It's a little bit like dropwise of neutron. So when this happens, the nuclei can take their time, do their job slowly, absorbing neutrons slowly. And whenever the nuclei think, I'm saturated, I'm full, I want to decay, then it can take time to decay. And then absorb and decay. Unless the beta decay or the electron capture, it has longer half-life. Otherwise, these processes sort of take place at the same time, and they are relatively slow compared to the R process. They generally produce the stable isotope at the upper left of the band of stability. Stars. Now it is the final part, the consequence of nucleosynthesis. This is the abundance of nuclei in the universe. This is a figure from the textbook. Here we have N plus Z. This is basically atomic weight. And this is the relative abundance of nuclei. What I want to ask first is, how do you explain the zigzag here? And second, how do you explain the peak here?
就当那个 particle number 越小的时候，它的那个相对风度会比较大。显示在铁56的时候会多，应该是可能就是因为那个核融合最后的反应到56。我的想法是这样。
那你有没有看到这边差值都是什么？
都是4。
为什么？
因为核融合就是两个碰撞，然后最后变成，就是以氢为例的话，两个氢碰在一起，然后最后变成4的氦。
所以这个跟这个中间差的是氢还是氦？
氦。
氦4。My first question is, how to explain the zigzag here? There is a difference in mass of 4. And when you recall what you have learned, the nuclei which has a mass of 4, it is helium-4. And helium-4 is the second most abundant material in the universe. To form larger nuclei, you basically involve helium-4. That's the reason why you always see a difference in 4. Why we have a second peak here? Because this is the end product of nuclear fusion. Now we have a closer look. What are the atoms here? They are basically the most abundant elements in the universe, okay, aside from hydrogen and helium. They are carbon, oxygen, neon, magnesium, silica, sulfur, argon, calcium. I don't know if any of you have been asked by other professors, what are the most abundant 4 elements on Earth?
系氮吗？然后铁、氢吗？
So he gets silica, iron, nitrogen. If I want to provide some hint, apparently the most abundant elements on Earth is here. It's highlighted here. When we talk about the Earth, it is not just the atmosphere or the outer surface of the Earth that we are talking about. We are talking about the whole Earth. You want to answer again?
细铁，碳和氧啊。
That was a guess. Okay, thank you. You might guess maybe that's these four. 1, 2, 3, maybe magnesium or iron. That's your intuitive guess. Carbon, oxygen, neon, iron. However, there's one thing you need to consider. Our Earth, it is not large enough to keep gas. Many gas are lost. So if I would guess the most abundant material on Earth, I should probably guess hydrogen, right? You guess hydrogen. However, hydrogen is very rare on Earth. And you didn't guess helium. I already told you how expensive helium is. Why? Because the Earth is too small. These most abundant gas, they are gone. Long time ago, they are gone. So what are the most abundant elements on Earth? Iron, of course. We have an iron core. Silica, magnesium, and oxygen. Why? You can imagine that they are all part of the solid Earth. Why not this carbon? Because it's barely involved in solid Earth. And why oxygen? Because oxygen is kept in the form of silicate. So silicate has a lot of oxygen. And these are the so-called alpha particle nuclei, because we know alpha particles is helium-4. Lastly, let's look at our sun. This is atomic number, and this is abundance in logarithmic scale, which means it has much, much more hydrogen and helium than all the other elements. Then you also see this zigzag. Question, our sun, what is it doing now? It's a main sequence star. The nuclear reaction within our sun is hydrogen fusing to helium. But when you look at our sun, it has a wide array of elements ranging from beryllium to uranium. So why does the sun have elements heavier than iron?
是宇宙其他的陨石撞到上。
The mass of meteorites too small to create this. 有没有什么想法啊？我觉得刚刚那个陨石撞击还蛮有创意的。
发生什么爆炸之类的吗？
Maybe as like on Earth we have a heavy element because we got it from supernova and all. Maybe some element from supernova just went to the sun, and then yeah, maybe others are from decay or something like that from this element from supernova.
Exactly. The sun got it from supernova explosion. We also have this element. The planet has zero ability to create any of this. But why do we have this? Supernova explosion. Okay, so I think that's what you need to know from the nucleosynthesis. Assignment 3. You will need to prepare questions for our next topic, planetary systems. So based on previous students, they somehow tend to dislike this topic a lot. You have to answer these questions. First, what are chondrites? You need to look up in the textbook. Within chondrites, there is another class called carbonaceous chondrites. What are they? Then, explain figure 5-4. Here, this is the relative abundance in carbonaceous chondrite. And here, it is relative abundance in the sun. Here you see these are apparently the abundance of these elements in this material and this material. And the solid line here is 1-to-1. So you see they agree with each other very well. Why? What is the y-axis? Do not just answer this. You have to explain how is the abundance quantified. What does the similarity in the composition between the sun's atmosphere and carbonaceous chondrites tell us? So why can we find such a good agreement between this material and this material? What's the sense does it make? So that's what you need to answer in your assignment.